Okay. Okay, so first so who will give me a good the definition of a specific latent heat of vaporization? What do we mean by it? Quantity of heat needed to change unit masses from liquid to vapor without change in temperature. Yes, yes. So specific, why do we call it a specific? Because we're talking about unit mass, remember? Specific is when we are talking about unit mass. So specific latent heat of vaporization. Latent means hidden, and vaporization means energy required for the molecules to change from liquid to vapor state or the gaseous state. So when we put all these words together, we will come up with the definition that it is the amount of energy which is required to convert a unit mass of substance from liquid to vapor without change in temperature. So why do we call it latent? Because it is hidden. Why? What do we mean by hidden is that it cannot be measured because it is not detected by the thermometer. And we discussed in our previous classes why it cannot be detected by thermometer, because the average kinetic energy remains constant, okay? And it is the average kinetic energy which is measurable by the thermometer. And so it is the potential energy which increases. And by potential energy, I mean to say that the distance between the molecules increases, and that like sort of, thinking of the molecules as balls which are joined to each other via elastic band. So the farther you will pull them apart, the greater will be the recoiling, and the farther will be a greater will be the force in the elastic band trying to. So think of that force. Think of force in the elastic band as the potential energy. So the farther apart the molecules are forced, greater is the potential energy until they snap until the elastic band is completely snapped, which means the molecules are now completely free from each other and they have turned into gaseous state. So I talked about this in detail in my last class. So this was just a recap. Okay, so once we have understood now how do we measure the specific latent heat of vaporization of a liquid. Now we make use of the law of conservation of energy. And what is that? The law of conservation of energy states that no energy is created or destroyed, but energy only is transferred from one form to another or from one system to another system. Okay, and so the total energy within a closed system stays constant. We don't have energy disappearing. Okay, we do not have energy appearing all from nothing. So energy in the whole universe, the amount of energy is constant. So making use of that, we know that the energy supplied by heater is equal to the energy absorbed by the liquid. Okay, I did send my new link in the group. Okay, let me send the group again. Oh, sorry. Oh, I'm so sorry. Okay. Okay, so no, it's the same. Guys, always use that link, which I always use. I mean, the one that I usually use, always use that link for entering into the class. Okay, that is the meeting ID that you get when I log in through my device. Okay, so it's okay, I'm recording, so those of you who might have missed, they can listen to the recording. Okay, so now, do you think this assumption is 100% true? Do you think this assumption is 100% true? Energy supplied by heater is equal to the energy absorbed by liquid? Yes, it is not true. So there are some flaws in this. Yes, some of it is lost to the environment. Exactly, very good. Some of it is lost to the surroundings, and so we have to, now in our experiments, we have to make sure that we minimize that for this to be true. For this to be true, we have to make sure that the energy loss to the surroundings is minimized. If not completely eliminated, should be at least minimized. Okay. Now so we will now deal with the equations. How do we get the energy absorbed by the liquid, and what equation will tell us, I mean, how do we calculate the energy supplied by heater? So let's talk about the energy absorbed by the liquid first. How can we calculate that? Now, we talked about the specific heat capacity and, specific latent heat of fusion and melting and everything in our last classes. So this is the same idea. So if we know the energy required to raise the temperature of any mass, the mass that we are using for our experiments for, in the lab, I'm giving it a variable M. It can be anything. It can be 5 grams, 100 grams, 50 grams, whatever, okay? So that energy, if I can calculate that energy, that will be the energy which is required to raise the temperature of mass M, okay? And so the difference is final temperature. I mean, by what temperature? This difference. So we will record the initial temperature, meaning the temperature that we started with, and the final temperature, okay? That at the end of our experiment, okay? So I'm giving the variable Q to the energy required to raise the temperature by a specific amount, which is defined by this of mass M, okay? And that M can be any value. Therefore, using this ratio method, the energy required to raise the temperature by 1 degree Celsius of 1 kilogram would be, I will cross multiply, the ratio method. So Q multiplied by 1 is Q itself divided by the mass and the temperature change, right? I did not write the temperature change. Why? Because we are talking about vaporization, right? So there is no temperature change during phase change, okay? We know why, we have discussed it. So therefore, because there is no change in temperature, we omit the change in temperature part. So what we are left behind with is this. So this is the energy required to raise the temperature, to change a 1 kilogram, let's suppose 1 kilogram, or I think it's 1 gram, to change unit mass. Okay, they have mentioned unit mass. This is the definition. So specific latent heat of vaporization to change unit mass. Now that unit mass can be gram, can be kilogram, whatever you're dealing with, but your book, I have noticed, uses grams. So we'll stick to grams, okay? I wrote kilograms here. So, but it can be grams. So the energy required to change 1 gram of liquid to water would be Q multiplied by 1 divided by the mass. So if mass requires this much, 1 gram would require Q multiplied by 1 divided by M. And I omitted the temperature change because there is no temperature change when we're dealing with vaporization. Therefore, if I cross multiply, so this is the energy absorbed, right? This is the energy absorbed. So energy absorbed is the product of mass. Q stands for the energy absorbed, okay? Is the product of mass and the latent heat of vaporization. Okay, energy absorbed by liquid to vaporize is the product of mass into the latent heat of vaporization. So this is the equation that we will use to calculate the energy absorbed by the liquid. Okay, now what equation should be used to calculate the energy supplied by the heater? Yes, Amna, I do realize that I did give you this assignment to explain this experiment, but because you did not verify with me, you did not confirm with me. So, I just went ahead and I did it myself. So it's okay. It's okay. We have lots of work to do. And so, I mean, I have lots of questions for you guys, so you can go ahead and solve them. Also, suggest to me, what should I do in my next physics class? Should I do the past paper questions of this chapter, specific latent heat and everything? Or should we move on to gas laws? Or should we do gas laws after the past paper questions? So went ahead, go ahead and let me know, okay? Nobody wants past papers, everybody wants to move ahead, gas laws. Okay, yeah, it's up to you. I can do whatever you want, you guys want. Okay. So So what is, we can do the past papers even after the gas laws. So, we can finish gas laws, because after gas laws, we'll be done with our whole course of grade 8, alhamdulillah. So we have finished grade 8 course for physics and biology. Only chemistry is left, the mole thing. Yes, so after that, we'll be done, inshallah, with grade 8 course. Okay, what is the energy supplied by water? Okay, sorry, by heater. Now, heater is an electrical appliance, and when we're dealing with electrical appliance, we can use the quantity power, right? So how do we calculate power? We divide energy by time, okay? And so we are interested in energy supplied by the heater, right? Energy supplied by the heater. Okay, Atika, we will do gas laws because majority of the people are saying gas laws. So let's do gas laws. And after that, we will do past papers of all the chapters combined. Okay, and I also want to do the questions at the end of this book. The past paper questions that they have given at the end of your textbook, I want to do them. Okay, so energy is the product of power and time. Okay, now how do we calculate power? We have these 3 equations from your electrical physics, if you remember. And if you don't remember, you can go back, read those chapters, and then be convinced that power is equal to the product of voltage and current, and the square of current and resistance, and square of voltage divided by the resistance. So if you have any two of these, either you have VI, or you have IR, or you have VR, or any two of these, you can calculate power. Okay, and then you also need time, right? Time can be measured using a stopwatch. Okay, so the instruments, the quantities that you require. Now plug in these into the equation, our equation. Energy supplied by the heater can be given to us by this. Okay, VI is power, so we substituted power by VI and we multiplied it by time, which should be equal, according to the law of conservation of energy, to the mass and specific latent heat of vaporization, right? So this is what we want to find out. So we have to know these 4 quantities. So our laboratory experiment should be planned in such a way, and the apparatus should be such that we get these 4 quantities, right? So voltage and current can be found out by using a circuit like this. Okay, the circuit is given on page 93. So this is the electric heating coil, and it is attached to this circuit. The ammeter is going to give you the value for your current. Voltmeter is going to tell you the voltage. And so that's all, V and I. So you will get V and I, and you can plug in the values for V and I. Time with the help of a stopwatch, and then mass, and we will talk about the mass. Okay. Now, I got this, this experiment that is mentioned in your book is rather complicated, but it is more efficient because it accounts for the loss of heat to the surroundings. They're using felt lagging, and they're using a jacket of vapor, so that is minimizing the loss of energy to the surroundings. So, I want to explain you the easy experiment. What are we trying to do here? Simple. So keeping that equation in mind, which is VIT is equal to M into LV. Keeping this in mind, all we want is, this can also be, if some of the heaters have power written on them directly. You don't need VI. So let's suppose we have the power given. So power multiplied by time and M into LV. So keep the equation simple. Okay, power, time, mass, this we have to find out. Okay, so this is easy, simple apparatus. Okay, you can do this experiment this way as well. But yes, this won't be accurate. Why? Because you did not account for the heat loss to the surroundings. This is a simple container with some mass of water boiling, and we're using an electric heater, okay? And assuming that this electric heater's power is labeled on it, and we have kept this container on a mass balance, So as soon as we see bubbles, as soon as we, LV stands for the latent heat of vaporization. That's a symbol used for the latent heat of vaporization, okay? So as soon as we see the bubbles forming, we know that boiling has started, right? So as soon as you see the first bubble forming, you turn on your stopwatch because that means boiling has started. Vaporization, I mean, what you're trying to measure that process has started, okay? So you turn the stopwatch on and you record the mass reading immediately because that will be your starting mass. That will be your starting mass, the mass that has started to boil. And then let's suppose you waited for 10 minutes, 15 minutes, or whatever, okay? You can even wait for this whole water to dry up. It's up to you. So after that, for example, 15 minutes. After 15 minutes, you turn off the stopwatch and then again you record the readings. So the difference between the two readings would be the mass of water that evaporated. You can plug that value in. The difference between the final and the initial will give the mass of the water that evaporated. You can plug in that value in this equation. You have the time from your stopwatch and you have the power from the labels of the electric heater. Simple, you can find the latent heat of vaporization for water this way. But this won't be accurate for many reasons. One is that we did not have insulation. Second, what are the other flaws in this? What are the other flaws in this? Amna. Okay, Amna, I'll unmute you. Yes.
Yes, because there's no lid on the top, so the the vapors escape.
Okay. And is that it?
Yeah, and there's no sheet of insulation around it, like the jacket of vapor, as well as the the there's no way of condensing the water properly.
Yeah, so there's no lid. Yeah, so there's also loss of heat evaporation. Okay. Yes, so that's a good point, and there's no insulation. Right. And what else? What else?
Miss,
Okay. Okay. So and then we are not even using a thermometer. So we were just relying on seeing the bubbles. We were just relying on seeing the bubbles, right? So that's another problem, right? Okay. So so how are we going to improve on this? Now let's move on to the reason why I explained you the simple experiment is so that you understand the basic idea, and then we will talk about the extra precautions that they have mentioned, that they have done in this experiment in your book. So the first step, uh, towards improving this experiment is that we're using felt lagging. I hope you understand the meaning of the word felt lagging. Felt lagging is insulating the container, okay? Insulating the container to minimize heat loss to the surrounding. Second is that we cover the mouth of the container by a stop bung, by a stopper. This is stopper that they're using. But remember, they are not allowing the vapors to accumulate. I mean, they are not, I mean, we have holes here. There are holes here which allow the vapors to move into this jacket, which is surrounding this whole container. And this jacket, after, some evaporation and after boiling, will be filled with vapor. And so it would form a jacket of vapor, which will further insulate this container from the surroundings. And then these vapors are made to pass through this condenser, where these vapors will condense into liquid, and that liquid will be collected in a beaker, the mass of which can be measured. So we will measure this condensed liquid, okay? Now, in the simple experiment that I just mentioned, I was just simply subtracting the final from the initial, and I was getting the mass of water that evaporated. But here they are condensing it and then they're measuring it. So which do you think is better, is more efficient? Now, I think this is better. This is more efficient, you know, the one which is mentioned in your book. But in order for this water to be exactly due to, you know, like we don't want to we don't want to miss the vapors that are still in the jacket, right? We don't want to miss the vapors that are still in the jacket because they also vaporized. So in order to eliminate that flaw, what they did was that they waited for that moment when the rate of dripping is constant. The rate of dripping is at a constant rate. So for that, you have to be extra careful while observing the rate of this dripping, because this rate of dripping has to be constant, meaning that per unit time, same number of drops. You should have same number of drops per unit time. So you have to be very vigilant, and you have to actually, you know, calculate the rate of dripping. So that's difficult. Okay, so this is more accurate, but this is more difficult. And so once you get that rate, once the dripping rate gets constant, you know that now the rate of evaporation or the rate of boiling is equal to the rate of condensation. The rate of boiling is equal to the rate of condensation, right? And so when that point is achieved, when the rate of evaporation is equal to the rate of condensation, all the energy which is supplied by the heater is being used to to provide the potential energy. All that heat which is being provided by this electric heater is being used for increasing the potential energy. I mean, we have eliminated the component of kinetic energy, right? And so once that rate gets constant, we turn on our stopwatch, and then we turn it off after like 15 minutes, and we measure the mass which is collected in this beaker. So that will be the mass of a steam. That will be the mass of a steam in that time interval. Okay? And then we can get V and I from the ammeters. Okay? Okay, so I hope I made sense, and you plug in the values, and then we can get the latent heat of vaporization for water. So let me check the chat window if you guys have asked any questions. There is no condensation back, so no balance of mass. I did not understand how I have to ask question. Abdul Wadud Farhan. Okay, is latent heat the least required heat for evaporation? No, latent heat of vaporization is the amount of energy which is required to convert liquid into vapor without the change in temperature. Okay, the condenser is to condense the steam so that it can be collected in the liquid form in the beaker. Okay, let me check. Okay. There is no condensation back, so no balance of mass. I did not understand your question, Amna. Okay, Abdul Wadud Farhan, I will unmute you. Maybe you want to ask a question. Okay, let me. Yes? Yes, Abdul Wadud. Okay, maybe you don't want to. Okay. Okay, let me give a chance to Amna. She wants to. Okay, Amna. Yes?
Yeah, I was just saying that I was just telling you that there's no You asked like how it is how it is better. How does it? How can we change it into a better way? So in the one 22.6, there is no condensation, so some vapors might be lost, and when we condense, all the water is again turned into the liquid, and it is cooled down, so it is easy to take out its mass.
Right. Right. Okay. Okay. So Abdul Wadud Farhan, did you? PT is equal to MLV. Please explain. Ahmad Azam, explain what? What do you want me to explain? What's the? Okay, Abdul Wadud Farhan, I tried to unmute you, but Okay, let's move on to the end of chapter questions. Okay. Ahmad Azam, please let me know in the chat window, what do you want me to explain? You just wrote, please explain. Okay, write down in the chat window what you want me to explain. If there's any particular point you did not understand. Okay, let's move on to the end of chapter questions. Okay. Okay. Question number 1, I wrote it down for you so that you know the question is right in front of our working. So, how much heat will change 10 grams of ice at 0 degrees Celsius to water at 0 degrees Celsius? How much heat, I'm repeating, how much heat will change 10 grams of ice at 0 degrees Celsius to water at 0 degrees Celsius? So, you know, an easier way, a good way of solving such questions is to make a heating curve. Make a heating curve. Ahmad Azam, your question is, how can we evaporate without changing temperature? At the boiling point, the energy which you are supplying is being used to pull them apart. I'm sure you are attending this class for the first time. Your question is telling me. Your question is telling me that you are attending this class for the first time and you did not attend my previous classes. So you got to do that first. Okay? You do that first, read the book, listen to my lectures or any lectures you like, read the book, do your own homework, and then if you don't understand, then you ask me. I wrote the question wrong. How much heat will change 10 grams of ice at 0 degrees Celsius to water at 0 degrees Celsius? Yeah, that's the question. Amna, what's the question in the book? I'm doing 1A. I'm doing question number 1A. Okay. So how much heat will change 10 grams of ice? So a good way of solving such questions is when you make a heating curve. It's, you know, you cannot go wrong if you make a heating curve. Let's follow this. So easy, solid, okay, the temperature will rise and then you have melting and then liquid and then boiling and then gas, right? So this is easy. Now, remember, boiling, the line of boiling should be longer than the line for melting. Okay, the line for boiling should be longer than the line for melting. Why? Because vaporization requires more energy and therefore it takes longer. Okay, melting requires less energy. It is a faster process, meaning it takes a shorter time. Now, so the question is asking 10 grams of ice. So my 10 grams of ice must be somewhere here at 0 degrees Celsius. So 10 grams of ice at 0 degrees Celsius. So I know the ice in the question is here in the heating curve. 10 grams of ice at 0 degrees Celsius, because this is 0. Okay, this is the melting point. This is 0 degrees Celsius and this is 100 degrees Celsius. Okay, so how much heat will change 10 grams of ice at 0 degrees Celsius to water at 0 degrees Celsius? So that means here. Okay, so they are asking me to calculate the heat which is required to take the ice from this point till this point. From this point till this point. Okay, from this point till this point. I have to take the ice from this point till this point. Okay, so you can see that I am dealing with this and this is simple straight line. Okay, there is no change in temperature here. The temperature is constant. Okay, so that means I will be using this formula. And what is the process? Mass into, this is fusion going on, right? Ice to water, this is fusion. So latent heat of fusion. Okay, and then they have asked you to use the table 22.2. They have asked you to use table 22.2. Now table 22.2 is this. You know, for my ease, what have I done? If I'm using this table and note down the units, they're using grams, they're using joules, and they're using degrees Celsius. So make sure the units in your questions are also the same. If they are not, then you need to convert, right? Now, this is water, ice, aluminum. Okay, if they are talking about water's specific heat capacity, so remember, we will use this value if the temperature of the water is changing without any change of state. And specific latent heat. This is latent heat. That means when the water changes its state, meaning it will vaporize. So this is the latent heat of vaporization. They're talking, this is a specific heat capacity for ice. That means change in temperature of ice without change in state, without melting, okay? Only change, like for example, from -10 to from -10 to 0. From -10 to 0. So from -10 to 0, it is still ice. For example, -10 to 0. So there is no change of state. We're just increasing the temperature of solid ice without any change. In that case, you will use this value. Okay, this is what is specific latent heat for ice. That means this is fusion. This is the latent heat of fusion, meaning they're talking about melting of ice, because ice cannot evaporate, right? This cannot be vaporization. So this is melting. Okay, and this is this is fusion, this is vaporization. Okay, so I have written down the names of the processes, and I think you can, I've written down fusion, vaporization. Okay. Okay, so simple. Fusion is 340. Fusion is 340. I plug in this value, 340 here, 340 multiplied by 10, answer is 3,400. Simple. Joules is required to change 10 grams of ice from 0 to water at 0 degrees Celsius. Okay, second question. What quantity of heat must be removed? Do you guys want to do these questions on your own? And then right now, has anybody solved and want to explain right now? If anybody wants to explain and they have done it, please come forward and I will give you a chance to explain. Okay, so in the meanwhile, I'll go ahead and explain. What quantity of heat must be removed from 20 grams of water at 0 degrees Celsius to change it to ice at 0 degrees Celsius? So first of all, on the heating curve, we will try to understand what's happening. Can you hold this? See if anybody volunteered to explain. Okay. If I have unit in Fahrenheit, what will happen? No, they won't give you Fahrenheit, Abdul Wadud. Fahrenheit is not used in IGCSE, okay? It's an American unit. If I have Fahrenheit, okay. Isn't 0 at the bottom? What do you mean 0 at the bottom? Oh, yeah, oh, sorry. Yeah, good job. Yeah, you pointed out my mistake. Yeah, so this should not be, yeah, this is yeah, this is the y-axis, this is the x-axis. So this is something in minus, okay? My x-axis is crossing it in minus some. Or you can do this. Oh yeah, yeah. The x-axis should be, this x-axis should be here. Thank you. That's very observant of you, Mirab. Thank you. Yes, that's a mistake. Okay. So, okay. So how should I go about this? And y-axis is correct, right? So it would go, yeah. Okay. Yeah, cut this. Cut this. Okay. Thank you. Okay. So, okay. So what quantity of heat must be removed from 20 grams of water at 0 degrees Celsius to change it to ice at 0 degrees Celsius? So let me try to understand this question on this heating curve. Okay, 20 grams of water at 0 degrees Celsius. So my water is here, 20 grams of water at 0 degrees Celsius. So my water is here to change it to ice at 0 degrees Celsius. So same thing, but I'm going in the reverse direction. I'm going this way. In part A, I was going this way. In part B, I'm going the other way, okay? And they have doubled the mass. It was 10 in part A, now 20. But because the process is the same, I will use the same value, latent heat of fusion, okay? But this time, this is freezing. This is freezing, but remember the freezing point and the Melting point are the same, the process is the same, so I'll use the same value. 20 multiplied by 340 will give me 6,800 joules. Okay, so that's how we do it. Okay, then question number 2A. Anybody wants to volunteer? Did anybody try solving these questions? You guys have done this chapter, right? In your school with your teacher. Nobody volunteered. And you know what? I have a feeling you guys don't even listen to the videos. Yeah, I know that. Yeah. Okay. How much heat, this is question number 2, part A. How much heat is needed to change 5 grams of ice at 0 degrees Celsius? Asif, which school are you from? Asif, which school are you from? Vices, you haven't done this in school. My daughter has done it. Okay, how much heat is needed to change 5 grams of ice at 0 degrees Celsius to water at 50 degrees Celsius? Now, again, my heating curve, okay? I will try to understand what's happening. So 5 grams of ice. So 5 grams of ice is here at 0 degrees Celsius, okay, to water at 50 degrees Celsius. So here, yes, Mirab, I have made the same mistake. Sorry about that. Okay, you can correct it. But it's helping me and you know, it's helping us. So we are good. So ice at 0 degrees Celsius is here to water at 50 degrees Celsius. Now, so this is what we are dealing with, this. That means we're dealing with melting. And then after melting, we are even heating the water from 0 to 50. So we have two processes going on. Melting plus heating, okay? That makes the question a little complicated. So first of all, we will deal with melting separately, okay? Energy required for melting is, you know, mass multiplied by the latent heat of fusion, okay, which from the table is 340, multiplied by, you know, the mass is 5 grams, and the answer is 1700. Then, but that's not the end of the story. We are also heating from 0 to 50 degrees Celsius. So energy required for heating water from 0 degrees Celsius till 50 degrees Celsius. Now, this is simple heating without change in state. Okay, I'm taking the water from 0 to 50. Okay, so I will use the specific heat capacity for water, and I'm dealing with liquid water. Okay, so the specific heat capacity for liquid water is 4.2 according to that table. 5 is the mass, 5 grams multiplied by 4.2 into the change in temperature is 0 to 50. From 0 to 50. So change in temperature is 50. And so if you multiply all of them, you'll get this. From where did I get 340? 340 is from this table, 22.2. 340 is the latent heat of fusion for ice, because it was ice we were dealing with, right? Right. And then it melted into water, and so I'm now using the specific heat capacity for water. Yes, they will. Yes, Amina, you will be provided with these latent heat of fusions and capacities and everything. Yes, they will give you. You don't have to learn. By the way, by using them again and again in your practice questions, you will end up learning them, but they will be provided. And when they provide, please use the values which are given. I mean, which are provided. Don't use your own values. Okay? And also pay attention to the units. The units should be compatible with the units in the question. If, for example, they have given you this particular table which talks in joules, grams, and degrees Celsius, and in the question they've given you kilograms or kilojoules, then you need to divide that by 100 by 1000 to get into grams. I mean, you'll have to convert the units. Okay, then you add the two quantities and you will get the total energy required, which is required to heat 5 grams of ice from 0 to 50 degrees Celsius. Okay, That was question number 2, part A. Okay. Now let's move on to question number 2, part B. If a freezer cools 200 grams of water from 20 degrees Celsius to its freezing point in 10 minutes, how much heat is removed per minute from the water? Okay, so let's talk again. Let's look at our heating curve. Let's talk about where's the heating curve. Can I make a new heating curve? Let me make a new heating curve. Okay, so let me try to rectify my mistake. So let's see. This is 0. Okay, so this is solid. Okay, there's melting going on at 0. Then this is liquid. Okay, and then this is vaporization. I'll make a longer line. Okay, and then this is gas. This is temperature in degrees Celsius. This is time in minutes. Okay, this is ice. This is water. This is steam. Okay, now what is the question asking? What was the question? Yeah, if a freezer cools 200 grams of water from 20 degrees Celsius. So let's say my water is here, 20 grams at 20 degrees Celsius. Let's suppose this is 20. From 20 to its freezing point. Freezing point is this. So we are going this way. We are cooling it. In 10 minutes, how much heat is removed per minute from the water? From the water. That means we don't have to include the change of phase. Simple cooling, that's it. From 20 to 0 degrees Celsius, okay? Simple cooling, no freezing, okay? So energy removed for cooling from 20 degrees Celsius till 0 degrees Celsius. I will use a specific heat capacity of water. Why? Because there is no change of state. I'm just simply talking about cooling of liquid water, which according to the table is 4.2, the table which was given, and mass is 200 grams, okay, and change in temperature is from 20 to 0. So that means net change is 20 minus 0 is 20, right? So 200 multiplied by 4.2 multiplied by 20 gives me total of 16800. Let me double check. By the way, this answer is not the same at the end of your book. Okay, your book is saying 1700 joules. I don't know how they got this. My answer is this, 16,800. So this is in 10 minutes. Per minute, you divide this by 10. For per minute, you divide this by 10, and so you end up with 1680 joules, which is my answer. Maybe they rounded it off to the nearest 100. I don't know. So if you guys think there's any mistake, you are free to point it out to me. I would appreciate. I want to ask a question. Okay, where did you get 4.2? Come on, guys. Don't ask this. I told you I'm getting all these values from this table, table 22.2, okay? This is a specific latent heat of vaporization. This is a specific latent heat of fusion. Okay, this is the specific heat capacity for liquid water, and this is the specific heat capacity for ice. Okay, I'm getting these values from this table. Okay. So your book says that the answer is 1700 joules. If you know how exactly 1700 joules, please come forward and tell me. Okay, you can even private message me, and then we will discuss it in the next class. It's to what? Talha Sarfaraz. It's to 2 significant. IGCSE requires 2 significant figures. Moreover, wouldn't the unit be joules per minute? Yes, yes. Thank you very much. Yes, the units would be joules per minute. Yes, that's correct. Talha Sarfaraz, which school are you from? Can you please kindly tell me, because I did not know this about 2 significant figures. but I can see other answers which are more than 2 significant figures. So would they deduct marks if I write 1680 instead of 1700, or will that be accepted? Okay, I think they should accept it, but okay, good. They don't deduct marks. Okay, good. Okay. So let's move on. Question number 3. How long will it take a 50-watt heater to melt 100 grams of ice at 0 degrees Celsius? Again, same, energy supplied by the heater is equal to the energy absorbed by the ice, okay? At 0 degrees Celsius, meaning that there is no, there is no change in temperature. So that means we're talking about heat, melting, right? We're talking about melting, so we will use the value of latent heat of fusion. So power is mentioned in the question, directly log in the value. Time is what they are asking, how long, right? Mass is 100 grams, and so just plug in the values and it's easy. Time is 680 seconds. Okay, question number 3 is done, and then question number 4. You know, it would have been better if you guys had done it yourself. I would have been happier, but I don't know. Okay, some small aluminum rivets of total mass 170 grams and at 100 degrees Celsius are emptied into a hole in a large block of ice at 0 degrees Celsius. What will be the final temperature of the rivets? Now here you have to use your common sense a little. There's no calculation in here. Because you see, they have used the word small and large. That means the rivets are really small. 170 gram is their total mass. And they're put into a hole in a large block of ice. So there's no way that these rivets are going to get a temperature, any temperature higher than 0 degrees Celsius. There is no way. I don't know what a rivet is. I don't know. That's a good job. Google it. You guys are good at Googling. Google and let me know. Yusra, Google it right now if you can, and then share with us. Nails? Say it loudly. Yes, Sundus is trying to. Yeah, come on.
I'm not really sure, but like I guess it's the screw thing behind the nail. You know.
Yeah, okay, some sort of screw maybe, or some sort of nails maybe. Okay. So some small aluminum rivets of total mass. So there is no way that these rivets are going to. A rivet is a what? What? I can let me read the chat. Okay, good job, you guys are coming up with answers. I like it. They are like nuts for construction. Yes, so Sundus was almost correct. Okay, they are like a short metal pin or bolt for holding together 2 plates of metal. It's headless and being beaten out or pressed down when in place. Okay, I got it. You know, something like this. I'll show you. Something like this. Yeah, you know, like to keep the 2 things together, and then they are flattened. Something like this, I think. Yeah, okay. So because, you know, these rivets are so small and the block of ice is so large, and the ice, of course, the temperature has to be 0 degrees Celsius, or it can be even lower, but there is no way for these rivets temperature to go above 0 degrees Celsius. So the final temperature is 0. Okay, this is what I think. If you think there is any calculation behind this, please come forward and share with me, because I don't think there is any calculation here. So simple, because ice is 0, so therefore the final temperature of rivets is also 0. Okay, now the part B is asking, what is part B asking? How much ice will melt? How much ice? That means we have to calculate the mass of ice. So again, we will make use of the law of conservation of energy. Energy lost by rivets, because the initial temperature was 100 degrees Celsius, right? Almost the, yeah, it's pretty high. So that was the initial temperature, and final temperature is 0 degrees Celsius, right? So energy is being lost by rivets, they're getting cooled down, and energy is being gained by ice. And we will assume that they are equal to each other. So energy gained by ice can be calculated using the product of mass and latent heat of fusion. And energy lost by rivets will be mc theta, because there is no change of state going on because they are made up of aluminum. So we will use the specific heat capacity for aluminum again, which is obtained from table 22.2. Okay, the same table given in your book. Mass is mentioned in the question, 170, multiplied by the specific heat capacity for aluminum. Change in temperature is 100 to 0, right? So total change is 100. And when we multiply all these three, we get 15300. And then, you know, the rest is algebra, right? And the latent heat of fusion is 340. I divide it and I get 45 grams of ice. Okay. Then, is there anybody who wants to do the rest of the questions? Are you guys understanding? Or am I just, are you guys understanding? Are you guys with me? Please reply. Yes, okay. Okay, that's encouraging. Okay. Because you see, if a person keeps, you know, that's why I encourage you guys to go ahead and solve these questions. Otherwise, you know, I can just go on and on and on, and you know, you're maybe not, you know, yeah. So, okay, how much heat is needed to change 4 grams of water at 100 degrees Celsius to steam at 100 degrees Celsius? Okay. Have I made a heating curve? No. How much heat is needed to change 4 grams of water at 100 degrees Celsius to steam at 100 degrees Celsius? So even without drawing the heat curve, well, you can and you should, but you know, for the sake of time, I'm not drawing it. So you can see that the temperature is the same. So that means this is vaporization going on. And so there is no change in temperature. So this is simple mass multiplied by the latent heat of vaporization. The product of this and the mass will give you the energy required. So simple, 340 from the table, latent heat of vaporization, mass is 4 grams, and we get 9200 joules. Simple. Question number 5, part B. Find the heat given out when 10 grams of steam at 100 degrees Celsius condenses and cools to water at 50 degrees Celsius. Now for this, it is important to draw the heating curve. Okay. Again, okay, let's use this one. So what were they saying in the question? But isn't this fusion? Which question are you talking about, Amna? 5? Part A? No, that's not fusion. 100 degrees Celsius of water to steam. This is vaporization. Okay, so find the heat given out when 10 grams of steam. So 10 grams of steam is here. 10 grams of steam is here at 100 degrees Celsius, condenses. So that means we are going this way, and cools to water at 50 degrees Celsius. Is that right? Am I right? Find the heat given out when 10 grams of steam. So steam is here at 100 degrees Celsius. Okay, so this is wrong here, from here. At 100 degrees Celsius, because this is 100. So be careful. So from here, I'm going from here, 100 degrees Celsius cools to water. So there are 2 processes. This is boiling or vaporization, and this is cooling of water, liquid water. So I will calculate the energy required for, because I'm going this way, I will call it condensation and then cooling, okay? So there are 2 processes, energy lost during condensation and energy lost while cooling. For condensation, simple, multiply the mass by the latent heat of vaporization, because condensation is just the opposite of vaporization. So 10 grams multiplied by the latent heat of vaporization, I get this, okay? Then after all the water has condensed, now cooling part. From 100 to 100 to 50 degrees Celsius, from 100 to 50 degrees Celsius. So what would be the temperature change? 100 to 50, 100 minus 50 is 50, right? So again, mass would be 10. Now we are dealing with liquid water. So specific heat capacity for water, and then change in temperature is 100 minus 50. So this is my answer. And then the total energy is this added and this added, okay? 2100 joules plus 23,000 joules. What did I write wrong, Amna? It's 2300. Oh, okay. Okay, latent heat of vaporization. Oh, yes. What's the answer at the back? Check 5 part A. So I'm just going to check 5 part A. 22. 5 part A. What? I'm okay. 23 multiply 20 2300 by 4. Yeah, okay. 2300 by 4 is 9200. Sorry. So yeah, the answer is correct. I don't know how I got this, but yeah, maybe I multiplied with the same number, but I wrote down wrong. Okay, so we are done with question number 5. You want to do the rest yourself, and then let me know if you face any problem or you want me to solve. What do you guys say? Or are you getting bored? You will try? Okay. So we are left with question number, we are done with question number 5. Okay, and we are left with 6, 7, 8, and 9 we had done, okay, in our previous classes. So only question number 6 and 10 are left. Okay, so let's solve them in the next class, or what do you guys want to do? Can you do question number 8 only? Question number 8, Yusra, I discussed in the last class. Okay. In the next class, we will start gas laws. Okay, so go ahead and solve these questions, question number 6 and 10. And if you feel any difficulty, please let me know. And I will also solve it, and I'll post it in the group maybe, because we are out of time now. Okay. Okay, is there any question? Please ask. Okay, assalamu alaikum wa rahmatullahi wa barakatuh.